Good evening. My name is Francisco and today we're going to make an experiment. We're going to determine in which of the glasses does the ball falls faster. This one has water and this one has oil. So let's go with it. Okay. So as we saw, the ball falls faster in the glass that has water. This is because the oil has more viscosity and the viscosity reduces the speed in which the ball falls to the glass.
Hi folks, we will be doing today for Mass and Energy 2, the experiment 2 of 4, which is superficial tension. We're gonna need 1 or 2 shaving razors, 1 little pin, a napkin to dry them off, and 200 milliliters of water. You know, these little metal things. We're gonna place the shaving razor vertically into the water as if the edge was cutting the surface. The result is that it sinks, as you can see. Now the pin. I cut the head to reduce the weight. We're gonna place it carefully. It's supposed to stay in the surface, but for some reason it didn't. I guess it's too heavy. Now we're placing another razor, just like the first one, except this time we're gonna place it horizontally. Like this. And as you can see, this time it doesn't sink. Instead, it's sustained in the surface by the superficial tension of the water. Now to make up for the pin that didn't sink, I have a hair clip. If I drop it horizontally into the water, we can see it doesn't sink. It's also sustained by superficial tension. And the end. And now we have some questions to be answered. Is the surface of the water completely plane? Well, no, it's not. It's curved around the object and the surface. What can you observe in the 2 cases where the objects didn't sink? Well, we can observe the water holding the object, forming this sort of a curve around them. You can see it in the light reflection. What affects the way they fall into the water? If they sink or if they don't sink? Well, if I drop the object with the cutting edge facing the water, it will cut the surface tension and the object will sink. But if I place the object carefully, in a way it doesn't interfere with surface tension, the water will hold the object in the surface.
First, we have the materials. We have 2 eggs, 2 glasses of water, 1 spoon, salt, and water. Then, we have to add the water to the glass. Now, we're gonna add 12 spoons of salt. Now, we're gonna mix the water with the salt. Then we're gonna add the eggs to this glass and we're gonna see what happens. In this case, the eggs float because the density is bigger in the water with salt than in the normal water. The buoyancy force is stronger in this case. Ta-da! We finished. Yeah, we did it! We did it! Yeah!
Well, first, the materials. We are gonna need 2 syringes, one of 20 milliliters and another one of 10 milliliters. We need red furniture oil, a container, a small hose, a 5,000 grams object, a ruler, and some napkins just in case. First thing we're gonna do is measure the area of the syringe's piston. We take the diameter, which is 2 centimeters and 1 centimeter, respectively. Now we're pouring the oil into the recipient, careful to fill just enough to fill the syringes up to 3/4.
Parece sangre. Qué feo.
Now we're connecting the hose, one end to the big syringe and the other one to the small syringe. Next, we will observe what happens with the bigger piston when we apply force to the smaller piston. We have to fill the hose and the syringes. It is important not to leave air bubbles for the experiment to work properly. Now, let's see how much the big piston is lifted when we apply force to the small piston. What you can hear is the syringe lifting the piston when we apply a little pressure. Now if we invert the process, the small piston will also lift.
Más.
As you could see, when we apply a greater force, the syringe broke. Broke apart. This goes thanks to Pascal's principle. We can apply a greater weight here, and it will lift the same as in the other syringe. This way, we can lift much greater weights. And now for the questions to be answered. We have area of the piston of the small syringe, which is 0.007853, because the radius is 0.5 centimeters, which translated to meters, that's 0.005, I guess. And that raised to the second power and multiplied by pi, we have this result. And now area of the bigger piston, that is 0.031416, which is pi, because as you remember, the diameter was 2, so the radius is 1, and multiplied by pi, it gives us this. Now force applied to the small syringe, which is the force applied by the 15,000 grams block, we have it's 0.5 kilograms, that is 50,000 grams to kilograms, multiplied by 10, which is the force of gravity. We are simplifying it as 10, and it gives us as a result 5 newtons. That is the force applied, 5 newtons. And now what is the force applied in the piston of the big syringe? Well, it's the same as the small syringe because the system is connected. So the result is 5 newtons, just as the small syringe. And what is the maximum mass you can lift in the actual system? With an object collocated in the big syringe, well, as long as the syringe doesn't break, there is no maximum weight, because the weight you apply in one piston will be lifted in the other piston. That's why Pascal's principle talks about. Maybe the maximum mass it can lift would be the mass of the syringe itself, but it can hold more than that, as we demonstrated earlier, when the syringe broke. So it can take as much mass, as much weight as the syringe can hold, that is, until it breaks.